Alright, so now we're ready to go. So, Chapter 3. And we're going to do Chapter 3 in a little kind of a funky order, because then that gets the bad stuff out of the way first. Okay? So today we're going to solve systems. Chapter 3 is all about solving linear systems of equations. Okay? We'll do graphing, we'll do substitution, we'll do elimination, we'll do Cramer's rule, we'll do matrices, all in Chapter 3. Okay? We will also do systems of linear inequalities, which is going to be tomorrow's lesson. That way we get the graphing out of the two graphing sections out of the way. So we're actually going to do section 3.1 today and 3.3 tomorrow. So we'll get those two out of the way first, and then we'll go back to the stuff that you already know. Okay? So, in a linear system of equations, so a linear system of equations is multiple lines. Okay? And so it's wherever these multiple, meaning two or more, cross. Okay? That's the plan. Okay? So multiple lines. Okay? There are three potential outcomes. Okay? So if I have two straight lines, what are my three potential outcomes? They're going to intersect how many times? Once, right? Okay. So if they intersect once, which means they cross. So there would exactly be one possible solution. Okay. We classify that system. Okay. That's the funky wording for this chapter. The system's classification then is it is consistent. Whoa, tap the brakes. Consistent and independent. If the lines meet at one point, we classify that as a consistent, independent system. Okay. What's another way that those two lines could interact with one another? They're parallel. So what about parallel lines? They never intersect. Okay. So that would be a no solution case. When we have parallel lines. Okay. And we classify that as inconsistent. What's the last way, the third way, that two lines could be graphed? Right on top of each other? Because can they cross more than once? I should say it. Could they cross twice? Could two lines cross twice? No. And so then we've got, so they cross once, they don't cross, or they end up being what's called the same line. Okay? So if they graph one on top of one another exactly, then we call that infinite solutions. And if we were classifying that system, we would classify that as consistent. But now it is dependent. So there's our 3 possible outcomes. Pretty much this entire chapter. 85% of this chapter is right there. All right? So, there might be more than 3, but give me 3 ways that you could graph a line. What? T-chart. Pick 4 or 5 different x's, plug it into your function, get out the y's. Okay? That's one way. It's another way. What? But that's not going to graph me a line on my paper. I need to graph it on my paper. Yes, I would want to put the graphs of my lines on graphing paper. You are correct, sir. How? What? What? Find the intercepts. Very good. That was the one I didn't expect you guys to get. Yeah, using the intercept method. So my x-intercept is where y is equal to 0. And my y-intercept is where x is equal to 0. So this is some number comma 0, and this is 0 comma some number, which are 2 points. You really only need 2 points to make a line. What? Like, what do you mean use the equation? Put it in y equals mx plus b form. That's probably going to be your most common method, right? When you graph it using the y equals mx plus b form, what do? I get that you were putting it on graph paper. But what do? What's the starting point? Which is? B is a number. Well, that too. In this case, it'd be a number. What? So I'd plot the point 0 comma b. Okay. What do you mean you do the slope from there? Say it louder, Casey. So you use the slope, being that the slope is rise over run, to get more points, right? Yep. Now, very, 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 very important question. How? So I've plotted all these points. Right? Either I made a t-chart, or I found my intercepts, or I plotted my y-intercept, then I found a bunch more points using the slope. Now, what? How do I draw a straight line? Even though that's from the Department of Redundancy Department. I use something straight, right? So what are some things that can be straight? Edge of a binder, ID, a ruler, another piece of paper, okay, right? Bunch of different things. But do we need to draw these straight? Yes. It is extremely important that you draw these straight. Because remember, we're looking for that specific intercept point. Or that intersection, I should say, point. So it is imperative that you use something straight. Okay? Because if you try and draw this freehand, you might be off by a whole thing. And then you're going to say, Linz, I got this. Why is it wrong? I'm going to say, because you don't know how to draw a straight line. Okay? And I'm going to say, remember the first day of the semester, and I told you, and draw them straight. Okay? So, let's get into it. Okay? So, we are going to graph these two equations on the same on the same coordinate system. Okay? Then we're going to state what the solution is, and then we're going to classify the system. Okay? So, my question to you is this. How do you want to graph the blue line? 3x minus 4y equals 8. Do the y equals mx plus b in this one? Okay. Alright. So if I'm solving this one for y, then that becomes negative 4y equals negative 3x plus 8. Divide everything by negative 4 gives me y equals 3/4 x minus 2. Okay. So that tells me I'm going to go to my y-intercept of negative 2. My slope is rise 3, 1, 2, 3, run 4, 1, 2, 3, and 4. Rise 3, 1, 2, 3, run 4, 1, 2, 3, and 4. Fall 3, run negative 4. Down 3, run negative 4. Now, follow-up question to my question before of should I go all the way across my graph? Why? Because I have zero clue where it's going to intersect. So I should go, for sure, go all the way across my graph with my line. Okay. Second function, green now. How do you want to graph it? Pick something different. T-chart? Yeah. Pick values of x. So I would go 1, or I'd go 0, I should say. 2, 4. Okay. If I plug x equals 0 into that function, I get 4y equals 16, so y equals 4. If I plug x equals 2 into that function, I get 6 plus 4y equals 16, right? Which is 4y equals 10, which is y equals 2.5. If I plug 4 into that function, I get 12 plus 4y equals 16, so 4y equals 4, So y equals 1. Okay. My question to you is this. Do those lines intersect? Yes. Where do they intersect? At the point 4, comma 1. So that is my solution. Meaning, if I put 4 into both of my functions for x, I should get out y equals 1. And I do. Classification of that system, then, since they intersect in one location, that is a consistent independent system. Okay? You now 2 goes there, then slope of -3 is there. End up to be the exact same line. Okay? So, my solution then is going to be what? Infinite solutions, yes. My classification is? No. Consistent dependent. Okay. Try that one. Let's see. +2 is there, and then -4 is 2, 4. What you got for me? No solution. I like that. So that's classified as inconsistent. Okay. Try that one. So that's what I got. Solve the following system. So they end up being on the same line, so that my solution then is infinite solutions. My classification then would be consistent and dependent. Agree? Yeah, buddy. Oops. That way. Go for it. So I get that, which puts their intersection point right there, so that intersection point would be what? Negative 4. 4, 1, 2, 3, 4, 5, negative 5. So that means they are consistent and independent. Oh, I thought you were waiting for a high five from her. Or was she drawing on you?
She gave me Sam's smiley.
No, okay. Go for it. Last one. So I get that. So no solution, which is inconsistent. Yeah. All right. Page 156, 11 through 27 odds. That's 8 graphs and 1 non-graph, which equals out to the sheet of paper that I gave you. Okay? So while you were doing one of the earlier examples, I handed that out. And let's just say, that it is due on Thursday, January 25th. Due January 32nd.
Due January tomorrow.
Alright?